Greetings! We are presenting Practice 5, Enzyme Immobilization.
Introduction. First things first. Biotechnology has been great advances during the last years with the obtention of several products for feeding and pharmaceutical industries. The use of processes that are catalyzed by enzymes is increasing. Because of that, that person compared with the not biological catalyst. Immobilized enzymes are physically located in a certain definite region in the space. A bunch of using immobilized enzymes. Increase of the stability of the enzyme against pH, temperature, solvents, contaminants, and impurities. Reuse of components lowering the process costs. Capacity to stop the reaction with the elimination of the enzyme from the reaction solution. The product doesn't contain the enzyme. The possibility to design a reactor of easy operation and control adapted to the enzyme. Disadvantage of immobilization. Change of the conformation of the enzyme respect his native state. Create heterogeneity of the system support enzyme where they can exist different immobilized protein fractions with a different number of units to the support. Loss of enzymatic activity during immobilization. The biocatalyst is more expensive than the native enzyme. The immobilization methods generally are classified in two big categories: physical retention and chemical bonding. In two or three columns, adsorption is based on weak bond although Hudson defacing in processes. They are involved van der Waals force, ionic, and hydrophobic interaction, and hydrogen bond. Covalent bond is based on the enzyme and support cross-linking, producing a strong and stable bond. The covalent bond is formed between the functional group of the matrix of the support and the enzyme surface that contains amino acid residues. Microencapsulation. Enzymes are surrounded by semi-permeable membranes which allows the pass of substrate and product but not the pass of enzyme. Supports. They could be classified in inorganic and organic. And here we can see the different types of supports.
Objective. General, immobilizing the enzymes contained in extracts of amino acids obtained by liquid and solid fermentation. Materials and equipment. This is the equipment and materials used in the practice, and also the reagents. The methodology. First, we calculate the concentration for the support. Then mix 10 milliliters of enzymatic extract with 10 milliliters of solution with the lowest concentration of sodium alginate. Place in a container and in ice bath on a magnetic stirrer. Pass suspension through needle using peristaltic pump to form drops. Maintain the calcium chloride suspension with the spheres in stirring. Repeat steps 2 to 5 for the two concentration of sodium alginate. Wash spheres with this distillate water after each immobilization and refrigerate. Take 3 spheres of each sample and place them in 1.5 milliliters microtubes. Triturate with a glass pestle and add 0.5 milliliters of distilled water and vortex. Quantify total protein with Bradford.
Results and discussion. The observances shown in Table 1 were recorded after the measurement of the enzymes immobilized on sodium alginate. The equation 1 was used to determine the concentration in micrograms per milliliter and was compared with the initial concentration of the enzyme to obtain a yield. Equation 1: y equals 0.004 times x plus 0.0582, where y is the absorbance and x is the concentration of protein.
Results: due to the lack of ammonium sulfate, only the enzyme samples obtained from the extraction of the solid-state fermentation, commercial enzyme and enzyme obtained from S. cerevisiae were used as shown in Table 1.
Here we can see the average absorbance and the alginate immobilized enzyme concentration using the equation 1. Also, we are able to see the initial enzyme concentration and the yield that the absorption produced.
Discussion: immobilization and alginate beads has been used successfully in white wine fermentation and in the production of ethanol. An advantage of using alginate for immobilization is due to changes in the composition of the cells. By interaction with it generates that the catalysts become more active, and it is reported that the fermentation occurs at a faster rate with respect to the cases in which it was used free enzyme. Another important advantage of this immobilized system is that the support protects the enzyme from the action of inhibitors, heavy metals, phenols, and extreme temperatures. In addition, solids to be easier to handle allow better control over the catalytic activity in batch and continuous type reactors.
Sodium alginate is used to immobilize alpha amylase because it's a solution with divalent ions, as calcium. The alginate polymerizes because of the ions produce a cross-linking of the polysaccharides, and therefore the enzymes are trapped at the time the alginate polymerizes. According to a study, the percentage of immobilized protein with respect to the total protein obtained after purification is 70%. For the data obtained in the case of Aspergillus niger, the percentage of immobilization protein is 38.85%, and for Saccharomyces cerevisiae, 41.95%.
The difference that exists in the percentage of immobilized enzymes is due first to the fact that in the study the alginate beads were left in calcium chloride solution for 3 hours. Also to the volume used of this reagent differs from the procedure realized. Another factor that explains the difference is the percentage of alginate used, because this depends on the size of the pore, and this should be such that the substrate and the product can diffuse easily into and out of the alginate matrix. In the study, percentage of 4, 5, and 6% were used for the concentration of sodium alginate, with 4% being the optimum. So it's possible to say that the larger pore size will be the enzyme leakage through the pearls.
The size of the pores decreases with increasing concentration of sodium alginate solution. In other words, that by reducing the concentration of sodium alginate solution, the larger the pore size of the beads and therefore the leakage of enzyme to form the pearls will increase. In the practice, only 2% was used for the concentration of sodium alginate, which is below optimum 4%. So the concentration is lower, allowing the pores to be larger and therefore the enzyme to escape. Another study that supports the percentage of alginate which optimal results are obtained is the research carried out by Sakin Telar and Satdeep Xavier in 2012. Used different concentrations of sodium alginate and calcium chloride with 3% and 1 mole of calcium chloride being the optimal.
The yield of immobilization of the enzyme depends on the concentration of sodium alginate. The porosity of the calcium alginate beads depends on the type of alginate and the concentration of gelling agent. In the case of the practice is used calcium chloride 0.3 molar and 2% weight over for alginate, difference that can mark the low performance of our process.
As it is shown, we can see concentration of sodium alginate and calcium chloride with their yield of immobilization.
Conclusion: the immobilization of the amylase enzyme obtained from the solid-state fermentation commercial sample and of a liquid fermentation of S. cerevisiae was performed. Low yields were obtained due to the possible factor previously discussed. Due to a lack of material, it wasn't possible to obtain results of enzyme immobilization obtained by solid-state fermentation using rice or carrier.
Here's our bibliography. And that's it. Any questions, you can contact us through our email. And thank you very much.